Alright, hi. I don't know if this is going to work, but I'm going to try to teach you class that we missed on Wednesday. So I'm here in my kids' playroom with the whiteboard. So hopefully this will work. We're going to start off with example 9.5 on page 302 because we left off the week before talking about recoil velocity and how if something starts moving that way, then the other thing in that system has to start moving in the opposite direction. That's recoil velocity. So like a gun firing, a rocket shooting its rocket fuel out is what propels the rocket up. So recoil velocity. So we're going to do example 9.5 on page 302. So in an automobile accident, two cars slam into each other head-on. The first car has a mass of 675 kilograms. It's moving with a velocity of 19.3 milliseconds, while the other one has a velocity of minus 22.1 meters per second. The force of the collision is so great that the two cars stick together, moving as one mass. So assuming the friction between the road and the car is small enough to be ignored, what is the velocity of the two cars locked together? So we have our mass 1 is equal to 675 kilograms, and then we have our velocity 1 is equal to, let's see, 19.3 meters per second, and then our mass 2 is 895 kilograms, and the velocity 2 is minus 22.1 meters per second. Hopefully you guys can see that. So if we think about the system, we have our momentum at the beginning. Total momentum in the system at the beginning has to be equal to the total momentum of the system at the end, after the collision. Okay, so the momentum of the first would be mass and velocity, and then you have to have the other car, the mass and velocity of the other car. So that is our momentum before the crash. And it's going to have to equal the momentum after the crash. And so the momentum after the crash is the total mass, so it's mass 1 plus mass 2, times the velocities, which is what we are trying to find. The velocity is what we're trying to find. So this is a v that we're trying to find. And this is after. So this is the momentum after the crash. So you do the math, and it ends up being a negative 4.3 meters per second. So it's going in the direction of this second car. They both end up going in this direction because this momentum was greater, and so they end up staying in that direction, but pretty slow, 4.3 meters per second. Again, they have another example on page 303 about a truck getting grain filled up. And so empty, we have a mass and how fast he's going, 2.2 meters per second. And then, let me erase this. And then they tell us how much mass of grain he gets. And so they want to know how fast the truck will be going if it doesn't use gas or brakes once it's full of grain, using the conservation of momentum idea. Okay, so we have the truck empty, so mass of the truck is 1.2 times 10 to the third kilograms, and its velocity is equal to 2.2 meters per second, so not very fast. He's going slow so that the grain can fill his truck up. And then he adds the mass of the grain, which is 7.4 times 10 to the second kilograms. Okay, And the book wants to know what his velocity will be with his truck full of grain if he doesn't put the brakes on or add any gas. So, no outside force in the system. So the beginning momentum would be your mass of the truck and velocity of the truck. So these two times each other. So that's got to equal, now we're going to have the mass of the truck plus the grain, because the truck is full of grain now. So those two masses together times the velocity that we're looking for. So we solve for this velocity, and it ends up equaling 1.4 meters per second. That's with him not touching the brakes, just coasting along. Once his truck fills up, now there's more mass to be moving, so he has to go slower to conserve momentum. Everybody got that? I hope so, because you can't really ask me a question. So, key here though, you have to remember no outside force if you want momentum to be conserved. If he had stepped on the gas at all, that would have been an outside force, and it wouldn't have worked, right? So, let's see. Moving on to the on your own problems on page 304. We have 3 here. You can find the answers in the back of the module in your book. So I think I'm just going to pick one to do for you. Let's do the middle one, okay? So 9.7. The on your own problem 9.7. So we have a 75-kilogram astronaut making repairs on his ship in space and accidentally loses his grip. He floats away from the ship and to his horror finds that the tie line, which was supposed to attach him to his ship, has come undone. He floats motionless in space. Have you guys seen Gravity? It's crazy. Anyway, several meters away from his ship. So being a good physicist, he realizes that if he throws the wrench, that's a mass of 1.2 kilograms he's holding, away from the ship, the law of momentum conservation says that he should begin moving towards the ship. So if he can throw the wrench with a velocity of 10.1 meters per second away from the ship, at what velocity will he start traveling back to his ship? So let's think about the system. That's him and the wrench, okay? That's our system. So before he throws it, our mass times velocity would be the mass of the astronaut plus the mass of the wrench, right? Times his velocity, which is 0 because he's just floating and the ship is kind of floating away from him. And then now it's going to equal, so this is 0. Now we think about the momentum once he throws it. So now we have a mass of the wrench that's being thrown, and he throws it at a velocity of, what does it say, 1.2, no, that's its mass, 10.1 meters per second, okay? So we have the mass and the velocity of the wrench, but we also have the mass and velocity of the astronaut. And we want to know how fast he's going to start moving towards his ship once he throws it. So this is 0 over here, so we set these equal to the negative, so move 1 over. So that would be a minus mass of the wrench times velocity of the wrench, and we divide by the mass of the astronaut, and that will give us the velocity of an astronaut. And when you plug all that in, it ends up being just a measly 0.16 meters per second. So just throwing a wrench at 10 meters per second, it's not going to get him moving very fast. But it will start him moving in the right direction. And see how it has a negative? Because if the wrench velocity we designate positive, and our answer turns out negative, that means he goes in the opposite direction of the wrench, which makes sense, and which is what we want him to do. And that's our answer. Okay? So hopefully you guys get the idea of momentum conservation and how to use it in problems, okay? So now let's move on to angular momentum. So in previous modules, we talked about force and acceleration and all that in linear motion, and then we talked about rotational motion, and we kind of had to rethink things. So instead of force, it was torque, a force times a lever arm, and then we talked about rotational acceleration instead of linear acceleration. Okay, so the same thing kind of applies in the momentum world. So we've just been talking about linear momentum. Now, instead of calling it rotational momentum, though, we're going to talk about angular momentum. Because when you're traveling in a circle, okay, rotational, circular, to talk about your place, your position, instead of talking about it on an like in XY coordinates, you'd have to change things up a lot. So what they do is they talk about it with your radius and an angle, right? So if you're here on the circle, you denote that with this angle. And then if you're here on the circle, you denote that with this angle. And if you're here, you denote that with this angle, okay? So the reason they call it angular momentum is because you talk about position in terms of angle. So thus we have what's called angular momentum. But what exactly is it? So in your book on page 305, we have the definition. It is the rate at which the position angle of an object changes in rotational motion. Oh, sorry, that is velocity. That's angular velocity. So just like linear velocity is your change in position over change in time, your angular velocity, which they denote like that, is your change in your angular position over time, okay? So you don't really have to do anything with this angular velocity. He's just trying to get you to angular momentum, okay? So just how, well, let's remember our definition of linear momentum. We denote that with a P, right? Linear momentum is our mass times our velocity, right? And so our angular momentum, they denote as a capital L. Well, let's talk about how we did, let's see, how we did torque versus force. So in linear talk, force, we talk about force equals mass times acceleration, but then in angular talk, we talk about torque being a distance, a radius times your force, or mass times acceleration, okay? So for momentum, what we add here is just a radius, a distance, okay? So it's mass times the velocity times a radius. Do you see that similarity? Okay, this is angular momentum. Now, angular momentum is way more complicated than what we're going to get into in this module. So this is a very, like, skim the top, lots of simplification happening. But it helps to understand what's going on. So, this is what you really need to know. Angular momentum, L, is equal to mass times velocity times a radius. Okay? And then we need to kind of apply the law of momentum conservation to this angular momentum. So in the same way that linear momentum is conserved in certain situations, angular momentum can also be conserved. So there's a definition on page 307, the law of angular momentum conservation. If the sum of the torques, instead of the sum of the forces when we're talking about linear momentum, if the sum of the torques on a system is equal to 0, then the angular momentum never changes. So do you see how that relates to your linear momentum conservation? If the sum of your torques is equal to 0, then your total momentum can't change. Okay? Does that make sense? The change in momentum would have to equal 0. Okay? Alright, so he gives you kind of some examples. Let's talk about why a cat always lands on its feet, okay? Well, when a cat is falling and is upside down, he is a system, right? Just the cat. There's no really outside forces changing anything as far as his rotation, okay? So what he does is he uses his tail. He spins his tail one way, and so the law of angular momentum conservation means that something's got to spin the other way, which that means if his tail spins one way, his body spins the other way, and he can land on his feet and be upright again. Does that make sense? So you can also think about a figure skater. You know, the Olympics are on right now. I'm sure you guys have watched a little bit of it, maybe. When they're doing their little spins, if like they have their leg out or their arms out, they're spinning at a certain rate. Well, when they bring their arms in, what happens? They start spinning a lot faster, right? Because what they're doing is their hands, let's say their hands are the system, right? And they're spinning at a certain rate. And so this is the radius. Okay, we have the radius right here. And it's got a certain velocity and mass. Now, when you shorten this radius, your velocity has to increase to keep your momentum the same. Does that make sense? We've all tried it, right? On a spinning chair, when you're spinning and you bring your arms in and you go faster, and then you stick your arms out and you go slower. Okay? That is all the law of angular momentum conservation. Okay? Everybody kind of get that? So there's an example on the next page, 308. And we'll go through that real quick. And then there's an on your own problem, and we're done. So we didn't really miss too much on our little, on my sick day. By the way, my son doesn't have fever anymore, so he's good. Sorry I had missed class. Let's do the example. He says, a child's toy is made by tying a ball to a string and passing the string through a hollow tube. The tube is then twirled to get the ball moving in a circle. Once the ball is moving in a circle, the tube is held still and the string is pulled down through the tube so that the radius of the circle decreases. Suppose the initial radius of the motion is 34 centimeters. So we have a radius equals 34 centimeters. And the initial speed of the ball is 3.2 meters per second. So velocity is 3.2 meters per second. If the string is pulled so that the radius of motion decreases to 12 centimeters, then what's the velocity going to be? What's the new velocity? So we'll call that radius, initial radius, and initial velocity, and then new radius and new velocity. That's what we're going to find out. So, if angular momentum is conserved, we've got to have mass times the velocity times radius equal to the new mass times velocity times radius, right? Okay, the mass doesn't change, so it cancels itself out. Now we have the initial velocity, initial radius, so we just divide by the new radius. And and that's going to give us our new velocity, which when you plug in the numbers gives you 9.1 meters per second. Right? Okay, so it goes from just going 3.2 meters per second around in that circle, and when you shrink that radius, then it starts going 9.1 meters per second. So that increased velocity quite a bit. Alright, so let's talk about on your own problem 9.9. It's really just a think through problem, not a workout problem. So it says, in a cruel laboratory experiment, a mouse is placed near the center of a plate that is spinning. Okay, so this plate's spinning and the mouse is in the center. Okay, the mouse begins to crawl towards the plate's edge. What will happen to the speed at which the plate is spinning as the mouse crawls in that direction? So let's think of conservation of angular momentum. So you got the mass of the mouse spinning around on a plate. Now he's walking towards the edge of the plate. So what's getting bigger? Your radius is getting bigger, right? And angular momentum is equal to mass, velocity, radius. If your radius is getting bigger, what has to happen to keep your momentum conserved? You can't really change the mass of the mouse, so your velocity has to get lower. So the plate will start spinning slower as the mouse goes towards the edge of the plate, right? Okay, now on your own problem 9.10, a toy similar to the one in the example that we just did twirls the ball at a speed of 7.5 meters per second and a radius of 22 centimeters. If the string is adjusted so that the ball travels at 3.2 meters per second, what will the radius of motion be? So just like the example, we have an initial velocity and an initial radius, and those are 7.5 meters per second and 22 centimeters. And then we change the ball's velocity this time to 3.2 meters per second. Okay, so what will the radius be? That's the question. So we set our angular momentums equal to each other. Mass, the original velocity, and the original radius is equal to the mass times the new velocity and the new radius. Masses cancel each other out, so now we have this divided by the new radius will give you the new this divided by the new velocity now will give you the radius. And so plug those numbers in and you get 52 centimeters. Do you get that? So we started out with 22 centimeters. What did our velocity do? We slowed down the velocity, so our radius should increase, and that's what we got. We got a bigger radius, so means we're on the right track. Okay, so that is the end of Module 9. Next Wednesday we'll go over the practice problems and review questions, and I'll hand you the tests. So you'll take the Module 9 test this coming week, and we'll start on Module 10 Wednesday. Okay, so read Module 10 for me before class. Thanks. Bye.